Chapter 12, Earth's Interior. Probing Earth's interior. Most of our knowledge of Earth's interior comes from the study of earthquake waves. Travel times of P, or compressional waves, and S, or shear waves, through the Earth vary depending on the properties of the materials. Variations in travel times correspond to changes in the materials encountered. The nature of seismic waves. Velocity depends on the density and elasticity of the intervening material. Within a given layer, the speed generally increases with depth due to pressure, forming a more compact, elastic material. Compressional waves, or P waves, are able to propagate through liquids as well as solids. Shear waves, or S waves, cannot travel through liquids. In all materials, P waves travel faster than do S waves. When seismic waves pass from one material to another, the path of the wave is refracted, or bent. Seismic waves are structure. So abrupt changes in seismic wave velocities that occur at particular depths help seismologists conclude that the Earth must be composed of distinct shells or layers. These layers can be defined by composition. Because of density sorting during an early period of partial melting, Earth's interior is not homogeneous. Okay, so here, just an example of paths of seismic waves. So here, just showing our three layers of the Earth based on composition. Okay, so P waves, they could take a very strongly curved path. They can go a little deeper and get refracted or bent by the outer core, and bent again. They bend and enter the outer core, and then bend again to enter the mantle. Okay, so they can travel, they can go in and bounce off the inner core. Okay, so there are different paths seismic waves can take. Okay, the layers are defined by composition. The three principal compositional layers are the crust, the mantle, and the core. The crust is a comparatively thin outer shell that ranges from 2 miles at the oceanic ridges to 40 miles in some of the mountain belts in thickness. The mantle is a solid, rocky, silica-rich shell that extends to a depth of about 1,800 miles. The core is an iron-rich sphere having a radius of 2,161 miles. Now, when you define the layers by physical properties, then you get 4 layers. With increasing depth, the Earth's interior is characterized by gradual increases in temperature, pressure, and density, and that's going to change the physical properties of each of the layers. Depending on the temperature and depth, a particular Earth material may behave like a brittle solid, or might deform in plastic, in a plastic-like manner, or melt and become a liquid. Main layers of Earth's interior are based on physical properties and hence the mechanical strength. The lithosphere, or sphere of rock, is the Earth's outermost layer. It has the crust and the upper part of the mantle. This is a relatively cool, rigid shell. Averages about 100 kilometers in thickness, may be up to 250 kilometers more thick beneath older portions of continents. The asthenosphere, or weak sphere, is beneath the lithosphere in the upper mantle to a depth of about 600 kilometers. A small amount of melting in the upper portion mechanically detaches the lithosphere from the layer below, allowing the lithosphere to move independently of the asthenosphere. So it allows the plates and plate tectonics to move around. The mesosphere, or lower mantle, is a rigid layer between depths of 660 kilometers and 2,900 kilometers. Rocks are very hot and capable of very gradual flow. The outer core is composed mostly of an iron-nickel alloy. It's a liquid layer, about 1,400 miles thick. There's convective flow within that layer that generates Earth's magnetic field. The inner core is a hard sphere, solid sphere, raised about 2,000 miles. It's stronger than the outer core, behaves like a solid. Okay, so here's our 4 layers here: our solid inner core, our liquid outer core, our lower mantle, our asthenosphere, and our lithosphere. And then there's this transition zone. And this is just showing the speed of waves as we travel through. So the P waves are faster than S waves. And as you go deeper, the P waves tend to speed up. Okay, and then they tend to slow way down when they go through the liquid outer core and then speed up a little bit more through the inner core. Okay, the S waves are blocked by that liquid outer core. The MOHO, or Moravitic discontinuity, discovered in 1909 by Moravitic, separates the crustal materials from underlying mantle. identified by a change in velocity of P waves. The core mantle boundary was discovered in 1914 by Benno Gutenberg based on the observation that P waves die out at 105 degrees from earthquake and reappear about 140 degrees. The 35-degree wide belt is named the P wave shadow zone. Okay, so here let's say an earthquake happens here and P waves are traveling. When they get to about 105 degrees around the earth from the point of the earthquake, they stop. And you don't get any more until you get to about 140. So these two zones are the P wave shadow zones. Okay, so this is okay. Then so this carries with the bending and refracting of the P waves. So the fact that S waves do not travel through the core provides evidence of the existence of a liquid layer below the rocky mantle. Okay, so in this diagram it's S waves instead of P waves, and they can't travel through this liquid layer. So our shadow zone goes from 105 degrees all the way to 105 degrees. Okay. Discovery of the inner cores, predicted by Lehman in 1936, P waves passing through the inner core show an increased velocity, suggesting that the inner core is solid. Thinnest of Earth's divisions is the crust. It varies in thickness from 70 kilometers, and there's some mountain regions, to where the ocean crust is only like 3 kilometers thick. There's two parts to it. There's the continental crust and then there's the oceanic crust. Continental crust average rock density is about 2.7 grams per cubic centimeter. Composition is comparable to felsic igneous rock granodiorite. Okay, so it's in between the felsic granite and the intermediate diorite. The oceanic crust density is about 3 grams per cubic centimeter, composed mainly of the igneous rock basalt. The mantle contains 82% Earth's volume. It's a solid rocky layer. The upper portion is composed of ultramafic rock peridotite. There are two parts, the mesosphere, the lower mantle, and the stenosphere, or the upper mantle. The core is larger than the planet Mars. Earth's densest central sphere has two parts. The outer core is a liquid outer layer. It's about 2,200 kilometers thick, and the inner core is a solid inner sphere, the radius of 1,200 kilometers. Density and composition. The average density is nearly 11 grams per cubic centimeter Earth's center, approaching 14 times the average density of water. Mostly iron, with 5 to 10% nickel and lesser amounts of lighter elements. The origin. Most accepted explanation is that the core formed early in Earth's history. As Earth began to cool, iron in the core began to crystallize and the inner core began to form. Earth's magnetic field. The requirements for the core to produce Earth's magnetic field are met in that it is made of material that conducts electricity and is mobile. The inner core rotates faster than Earth's surface, and the axis rotation is offset by 10 degrees from Earth's poles. Earth's temperature gradually increases with increase in depth at a rate known as geothermal gradient. So this is what's causing the Earth's internal heat engine. It varies considerably from place to place, averages from 20 to 30 degrees Celsius per kilometer as you're diving into the crust, but then it increases slower in the mantle and the core. Major processes that have contributed to Earth's internal heat: well, heat emitted by radioactive decay of isotopes of uranium and thorium and potassium, heat released as iron crystallized to form the solid inner core, and heat released by colliding particles during the formation of Earth. Heat flow in the crust, processes called conduction. Rates of heat flow in the crust vary. Mantle convection. There is not a large change in temperature with depth in the mantle. The mantle must have an effective method of transmitting heat from the core outward. Okay, so here's this mantle convective flow. As a hot mantle rises, and as it cools, it sinks again. Okay, and it rises where there's a plume. Okay, so this is a convective cycle. Okay. Important process. Mantle convection is an important process in Earth's interior. It provides the force that propels rigid lithospheric plates across the globe. As the mantle transmits S waves at the same time and at the same time flows, it is referred to as exhibiting plastic, both solid and fluid behavior. Changes at Earth's gravity. Changes at the surface are due to Earth's rotation. Rotation causes a centrifugal force that is proportional to the distance on the axis of rotation. The shape is flattened slightly at the poles, and the equator is bulging out, resulting in weaker gravity at the equator. So here the equator is bulged out a little bit. So let's say a fisherman who weighs the same amount, fishing at the pole, he weighs 200 pounds, but where gravity is weaker at the equator, he only weighs 199 pounds. Okay, Earth's three-dimensional structure. Seismic tomography has three-dimensional images of structural variations in the mantle that are made using seismic waves. The continental lithosphere can extend hundreds of kilometers to the mantle. Cold, subducted oceanic lithosphere sinks into the base of the mantle while megaplumes rise upward from the core mantle boundary. Okay, so here's a seismic tomographic slice. It's cutting through around this line here. Okay, here's the Pacific Ocean. Okay, Atlantic Ocean. Here's North America. Okay, so here may be where there might be a plate being subducted. I'm not sure, but here the reds, the yellow through the red. S waves are slower. Variations are and then here the S waves are faster. The green through the blue. Okay, Earth's magnetic field is produced by vigorous convection of liquid iron in the outer core. The magnetic field is essentially a geodynamo caused by spiraling columns of rising fluid. It is primarily dipolar, so it's a north pole and a south pole. Patterns of convective change rapidly enough so that the magnetic field varies noticeably over a lifetime. There's Earth's magnetic field. It turns into this rotating fluid, turns our planet to a dipolar magnet. So here's the North Pole and here's the South Pole. This is how the lines of force, the magnetic field, radiate out from the Earth. The magnetic field randomly reverses. North and South poles swap directions. So the North Pole becomes the South Pole and the South Pole becomes the North Pole. Reversal takes only a few thousand years. Dipolar field significantly decreases in strength while this is happening. Reversals are important as the field creates a magnetosphere around the Earth that protects our planet from solar winds.